Hello guys, it's Johnny time and welcome to another smart contract hacking tutorial. In today's video we're going to tackle the 7th Damn Vulnerable DeFi challenge, Compromised, and we're going to use the most recent updated version 4 of Damn Vulnerable DeFi with Foundry. This is a super interesting exercise that is going to teach you about oracles, exchanges, and private keys in crypto. And without further ado, let's get started. Alright, Damn Vulnerable DeFi version 4 Compromise, here we go. While poking around a web service of one of the most popular DeFi projects in this space, you get a strange response from a server. Here's the snippet. So you got like a 200 OK response, HTTP response that looks cool. And we have some encoded data inside. Seems like two separate pieces of data that are not readable by human beings, but they're in some kind of encoding form. A related on-chain exchange is selling absurdly overpriced collectibles called DV NFT or Damn Vulnerable NFT, now at 999 ETH each. Absurd. The price is fetched from an on-chain oracle based on 3 trusted reporters, and we have the addresses of the reporters 1, 2, and 3. Starting with just 0.1 ETH in balance, pass the challenge by rescuing all ETH available in the exchange, then deposit the funds into the designated recovery account. So to summarize, we have here an NFT exchange. We got a weird response from one of its servers. It uses Oracle, 3 different sources, and we need to steal the ETH from the exchange. Let's get started. When I solve these challenges, I also want to show you how I think and give you some tips that help me tackle these challenges and in general perform better in smart contract audit reviews and security research work. So in this exercise, we have 1, 2, 3 smart contracts and 1 test file. And by the way, if you're not sure how to get started with Damn Vulnerable DeFi and this is a bit new to you, check out my first video and the whole playlist in general. I have a full playlist with all the solutions and the walkthrough videos. So this is the exchange smart contract, and we see that we use here address and reentry SIGAUT from OpenZeppelin. We import this other Trustful Oracle smart contract, and we import the Damn Valuable NFT, which is probably a wrapper of NFT ERC721. And we have some state over here, the token, the NFT, and the oracle, some predefined errors and predefined events. And the first tip that I want to tell you is that when I started looking at this challenge, there was no comments, no doc strings whatsoever. So what I like to do, I know that at this point, you might think you lack some technical knowledge to understand all of this with ease. That's exactly why I created this smart contract hacking course. Instead of piecing together scattered resources, you will follow a structured learning path together with hands-on exercises that simulate real-life attacks. When you get stuck, our Discord community with security researchers and fellow students is there to help. And once you've mastered everything, you will earn an official certification to validate your skills. Transform from watching tutorials to actually understanding smart contract security. Visit our website to start your journey today. So what I like to do is to use AI. I use Copilot, which is great. It integrates with VS Code, depends on your preference. You can use Cursor, Windsurf, whatever AI agent that you prefer. I give it the context of the file and I ask him, please add doc strings for every single function that will explain its logic. Make them concise and to the point. Okay, something like this. And then it gives me those nice notice, params, return, which is way easier to get some kind of initial idea about a function and to read it faster and understand it faster. This can work both in challenges like this or any smart contract audit that you perform. It's significantly going to help you to grasp the code and the code base faster. So as you can see here, all this added notice, return, this AI added for me, and it really helped me understand faster the contract. So we have here the constructor, and I can just read here, initialize the exchange with an Oracle and deploys an NFT contract. I don't even need to read the code. It summarizes it for me. Buy one, allow users to buy an NFT at the Oracle determined price. Okay, it returns the ID of the minted NFT. So let's review this function. We see that we need to send ETH to this function, and if it's 0, we'll revert. We use the Oracle contract to get the median price of the NFT, and we make sure that the message value we send enough ETH to cover for the price of the NFT that we got from the Oracle. And if we did, we use the ERC721 safe mint function to mint a new NFT. This is going to be its ID, and we send the chain. So in case the user sent too much ETH, we deduct from this ETH the price, and we send the change to the user and emit an event. Important thing to understand about Safe Mint is that it essentially, the ERC721 contract is going to issue a callback to the receiver, to the message sender, and the message sender need to implement this on ERC721 received function and return a certain hash, or this safe operation will revert. And by the way, this is a very interesting attack vector with reentrancy attacks, but this is out of the scope. This is something that we cover in the smart contract hacking course. We have a dedicated, awesome challenge just for these small vulnerabilities. So if you're interested, check out the smart contract hacking course. And in that case, this safe mint cannot be exploited for reentrancy attack because there is no state management here. So we cannot manipulate the state whatsoever. Even if we re-enter the function, we already pay the ETH, we get one NFT, and we'll have to pay again. So it doesn't really help us, and it's not really exploitable. We cannot really exploit here any callback or reentrancy issue. So we saw the buy one function, and we also have another sell one function that allows us to sell NFT to the marketplace, to the exchange. You will pass the ID of the NFT. It's non-reentrant. Oh, by the way, these functions are non-reentrant, so this external call doesn't make sense anyways. We cannot re-enter the function or the mutex will revert. So this function checks that the owner of the NFT is the message sender. It tries to see that the message sender approved the smart contract to spend this NFT so it can use later on the transfer from function. Then it tries to get the median price, again, like in the buy operation, from the Oracle, and make sure that this contract has enough balance to pay for this NFT that it purchases from the user, transfer the NFT from the user to the marketplace, burns the NFT, and send the ETH to the user, mints an event. And we have another last function here to receive ETH, another payable function. So the exchange is pretty straightforward. There is no vulnerability that comes in a first look that we can just see right away, but we see that there is more depth to the exercise. We definitely have to explore this Oracle contract because this is how the exchange determines the NFT price, both in the buy and the sell operations. So let's take a look at a Trustful Oracle contract, which is the Oracle, and it's a contract that has minimum sources, some hashes for roles, Trusted Oracle initializer. It has prices by sources mapping. It has an error defined, event defined, and let's see what happens in the constructor. So the constructor initializes the contract with trusted sources and optionally enables initialization role, and it receives the sources and enable initialization boolean. The sources is essentially a list of addresses which are the trusted sources that report prices to the Oracle contract, and we need to have at least one. We saw that this constant is 1, and it essentially grants the trusted source role to all the addresses that were passed in the constructor, and if enable initialization is on, it grants the role to the message sender that it can initialize the prices, I assume. Scrolling down a bit more, we can see the setup initial price. It's a function that sets up the initial prices for symbols from trusted sources can only be called once. So it just makes sense. Right after constructor, we have this initialize function, receives this array of sources, array of symbols, and array of prices. And only the initializer role that was defined in the constructor can call this function, and only once, because then we use this reannounce role at the end of the function and remove the role from the message sender. Here we have a check that the array length should be the same for all the 3 arrays because they need to match, and we iterate through the sources array and just set the prices based on the data that was passed to the contract. Then we have this post price function that essentially can be called only by one or two any trusted source that is defined in a contract, and it can just set the price for a new symbol. It calls this internal set price function that probably set the state and set the price of the source. Let's see. Yeah, so this is the function. It receives source, symbol, and new price. It just updates the state, the prices by source mapping, and emit an event with all the information about the previous price and the new price. So this was the post price and set price functions, and we have this get median price that this exchange uses actually. We saw it before. It tried to guess the median price of the symbol, and this function calls this internal compute median price function. Let's dive into it. This is another great example of how I use AI to understand contracts better. I initially didn't understand very well the algorithm of this compute median price, and I wasn't sure how it works. So I asked AI to create an example with numbers and show me how the algorithm works. So let's dive into it. Compute median price, internal function to compute the median price for a symbol. It receives a symbol, which is just a symbol, and return the calculated median price. Let's see what it does. So it takes all the prices for the symbol, probably from all the sources. It sorts it. Then if it's even list of prices, which means that we have even number of sources, what it does, it takes probably the center of this array and then returns the average, which is the median price. If it's an odd number of prices or sources, then it just returns the center of the array. Now, if you read this code and you are not sure about this algorithm, ask AI to organize it for you. And this is exactly what AI did for me. So it tells me, here is the example of how the median calculation works. In case one, we have odd number of prices. We have like 5 trusted sources that report 5 different prices. In that case, we first sorted this array from lower to higher number. So this one is a sorted, and then we pick the center. This is the median price, the number 8. That's what this code does in case we have odd number of prices. In case we have even number of prices, it does the same in the beginning. It just sort all the numbers and then pick the 2 numbers in the center. Let's make more space. Now it's clearer. So it picks the number 8 and 10, and it makes the average, which is going to be 8 plus 10 divided by 2. 18 divided by 2 is 9. So the median price is going to be 9. So this is how this function is going to select the price based on the sources and the prices that it has in state at the moment. Now that you understand both the exchange and the Oracle contract, we need to try to find a way to hack it, to manipulate the Oracle prices, manipulate the exchange, find vulnerability either in exchange or in the Oracle prices. So you read the contract once, you read it twice, but you cannot find any vulnerabilities. This is something that you're probably familiar with, and this is probably what happened to you in this exercise. And this is the reason Web3 hacking and smart contract auditing requires creativity and thinking out of the box. Now, if we revisit the exercise, we got a clue here that we got this weird response from the web application. And sometimes hackers are using Web 2 methods in order to hack Web3 application. We saw it many times, especially in the recent huge $1.4 billion Bybit hack. So we got this data from the server, and I'm not sure what is this data and how it looks like. So I can either search online or use AI and ask him to explain to me what this data is and if it knows how to decode it. And this is exactly what I did. I went to GPT and ask him, what does this data look like? Can you decode it for me? And let's see what GPT does. So we just give it the data, and it tells me that this data is probably Base64-encoded. Let's decode it together. And it wrote a small Python script to take the data and decode it. And it decoded the data for me. Now, this already looks more familiar. If you're familiar with blockchains, it looks like a private key. So essentially, this web server leaked the decoded version of the private key. I assume the source's private key, right? Because we need to do this exercise somehow. And maybe now we can use these private keys to essentially report prices from these sources. And we already know that there are 3 sources. So if we possess power on two of them, if we have power of 2 of the sources, this is enough to manipulate the Oracle price, because we already know that if we have an odd numbers of prices in the list, it's going to sort them and take the median. If we control 2 out of the 3, it means that we can definitely take the price because it will take the center, which is our malformed and malicious price that we just reported with a stolen private key. So our plan is to take those 2 private keys that we found, the leaked private keys, and then manipulate the Oracle price, make the NFT price very, very low, then buy it from the exchange, maybe even for free. Maybe we can even set the price to 0. So we buy the NFT for a very small manipulated price, could be 0, could be 1 way whatsoever, and then we sell it for a super high price to steal all the ETH from the exchange, the 999 ETH, and then sending it to the recovery account. Perfect. We have the vulnerability, we have the attack plan. It's not a classic smart contract vulnerability, but more like a Web 2 hacking method, but that's totally fine. All right, so let's see what we're doing over here. So we have these both private keys. This is our exploit in the test file, compromised t.sol, test compromised. And by the way, if at any point you get stuck, feel free to check out the GitHub repository with all the solutions. Feel free to start a repo, to fork it, to use it. All the exercises and the solutions are there, including all the tutorials of how to solve them. So we set here the private keys and then we create the sources, source 1 and source 2 based on these private keys. Then we deploy this new attack contract that we just created. I will show in a second how it looks like, but we deploy this contract and we send it our ETH because we need to use this ETH in order to purchase the NFTs. Don't worry, it's not going to be a lot of ETH. Anyways, we have only 0.1 ETH. So we pass all these parameters to our malicious exploit contract and we manipulate the price by using these 2 stolen sources, source 1 and source 0, and we set the NFT price to 0 here from these 2 sources. So now that we have like 3 prices, 3 sources, 2 of them are going to be malicious. We're going to sort the array, pick the center, which means that the price that the Oracle will report will be 0. Then we use our malicious contract to buy the NFT. We had to deploy this malicious contract because in order to buy an NFT, it's going to use the safe mint ERC721 function, and we need to implement the on ERC721 received function or the transaction will be reverted. So that's why we have another contract for that. We couldn't just buy the NFT here. And right away after we got the NFT, we changed the price again, this time to 999 ETH, all the balance that exists in the exchange contract. And we sell the NFT to the exchange, take the 999 ETH and transfer it to the recovery account using the recover function. So now that we understand the flow, let's dive into the attack contract and take a look at the buy, sell, and recover function. It's here, down here. This is the newly created attack compromised contract. And I wrote here that we need a contract since we need to implement the ERC721 receiver interface and get the callback after safe mint. And this is exactly what I did. I inherited from the ERC721 receiver contract, defined all the state variables, set all of them in the constructor, and this is the buy function. So in the buy function, we essentially just buy the NFT. We have to send 1 way, not 1 ETH, 1 way in that case, because in this function, in the buy one, it makes sure that we send at least something, so the message value cannot be 0. That's why we send here 1 way, and we get the NFT token ID, which we save here in the state so we can sell it later. Now, this is the sell function. We're simply just approving this NFT token ID that we previously bought to the exchange and then call the sell one function with this token ID. And we have this on ERC received. So when we do the buy operation, we can actually receive the NFT, and we have this callback and we have this fallback receive payable function to receive the ETH once we sell the NFT. Then we have this recover function that simply just send the stolen ETH to the recovery account. Now let's go to our terminal and try to run the compromise test. And we did it, the test passed. We completed the 7th Damn Vulnerable DeFi challenge, completely in Solidity and in Foundry. If you enjoy this content, make sure to like this video and subscribe to the channel and watch the rest of the playlist and the solutions. If you have any questions or you don't understand something, feel free to ask your questions in the comments section below. Thank you so much, and I'll see you in the next one.